What's up, guys? I'm going to be doing Facebook Hacker Cup qualification round. And what most of you guys might not know is that I'm going to use Java and Eclipse for this round. The reason is because in Facebook Hacker Cup, you're given the input file to the problem, and you're supposed to run the program yourself, and you get like 6 minutes to do so. And I've never run into the issue of Java being too slow to run the input within 6 minutes. And also there's the usefulness of if some exception happens in your Java program, like usually you'll know that something bad happened. It reports an exception. But then in C++, if you access and if you access like a non-existent element of an array, for example, then for example, if you access array of -1 index, then most of the time you won't know, the program won't stop and it won't tell you that something went wrong. So that's one reason why I'm using Java. And the last reason is just because I kind of want to use it. I barely get to use it in competitive programming, and I thought it would be nice to use it once in a while. So for this contest, it's a qualification round, so I don't really care about my rank. I've started really late anyways, over 2 days late, so I'll just be explaining, I'll be trying to explain my thought process more during this round. Okay, then let's start our first problem. Okay, so the first thing we should do is we should actually find which flights are allowed from the given I and O. And this should be pretty straightforward. You just need to check that, for example, if you want to know if the flight from 1 to 2 is allowed, then you check that I of 2 is yes and O of 1 is yes. Okay, after you find which uh like for each pair and each direction, after you find if the flight is possible, then what you can do is you can basically fix a starting point. And then let's say this, for example, the starting point is 3, and you want to know which flights can reach this. So first you just go to the left and you check that a flight from 2 to 3 works, and then if it works, you go left again. Maybe I should increase 3. Okay, so for example, if you start at 5 and then you find that 3 can go to 5 as well, and you try to find a flight from 2 to 3, but if you can't find one, then that means that 1 and 2 both can't reach 5. So and then after you do it for the left side, you do it for the right side as well. And yeah, this pretty much sums up the solution. I'll just make sure this condition is correct. So, or maybe I can do it outwards instead, because one row of the matrix, so the row I of the matrix stores all of the stores which country I is able to reach. So actually, if I print out the answer row by row, it makes sense to for each country to figure out which countries it can go to, instead of the opposite way around. Okay, I think that I've sufficiently explained like my algorithm. Now I'm just going to write it. And then we're given I and O. Call it A and B because like I is a common variable name for like indexes and loops, so I don't want to use that. Okay, then I find which flights are possible to the left, I guess. So this means we can go to the left. And this will be of length n-1. And we'll do the same thing for the right side as well. Now let's actually calculate these two Boolean arrays. So if we want to go to the left, that means the incoming country is like incoming country is I, and then outgoing is I+1. I think so, right? Yeah, okay. Wait, it's... Oh, okay, anyways, so we need to check that AI is equal to yes, and BFI plus 1 is also equal to yes. Then we can set, and that means this flight works. So I don't need a new loop for this. And then for right, incoming is I+1, outgoing is just I. Okay, now we have like the flights that we're allowed to use. Now we'll output the answer. So S stands for like the starting point. I'm supposed to use out. Okay, so this will be our answer for like this row of the matrix. And then to print the answer, we basically just iterate over the row. If it's true, it's just yes. Otherwise, it's no. By definition, answer of S is equal to true, because any country can reach itself. Okay, and then let's first go to the left. So left is equal to S. So while we'll try to go to the left, try to see if L-1 works. So first L-1 has to be like greater than or equal to 0. And then you have to be able to go left, yeah. So can left L-1. That means L-1 works, so we set it equal to true. And we have R as well. We want to check if R+1 works. So R+1 has to be less than n, and you have to check that we can go to the right. Okay, overall this looks good. Oh, they added this like copy feature. Okay, how do I compile this on run code? Okay, outputs look correct, so now I'm going to okay, now I'm going down the input file and like, oh shoot, I downloaded it in the wrong. Okay, I need it to be in like this folder. Input, and then I need to go over here and change Eclipse so that it's going to take in the input here. Let's run this, and yeah, everything seems to be good. So now let's get our output here. Let's validate. So, oh, there's a validation input. Okay, that's interesting. Oh, was it the same? No, it actually had additional test cases, which is pretty nice actually. So we have to give the output in source code. This is kind of annoying. Okay, and then I swear, like, I'm going to accidentally use the wrong input sometime. Okay, case 100. Output is from here. I don't even know where my source code is stored. You know, I'll just like create a new file. I don't know if this is safe, but okay, let's submit. Processing your submission. Okay, I think I got, yeah, I submitted this, so hopefully it'll be correct. I'll know by the end of the contest. On to the next problem. I want to say that it's always possible as long as... Wait, no. That's a bad assumption. I think the answer probably depends on like how many... the ratio of like the number of A's and B's, I think. Just an initial guess. Like you can't have too many A's, you can't have too many B's as well. So what happens if you have like so for example, if you have like n equals to 5 and you have 4 A's, no matter what you do, like you're going to reduce it to A, and then which will be bad. So let's start from n equals to 3, and or let's start from n equals to 1, and we can work our way back. So when n is equal to 1, we can either have 0 A's or 1 A. There are these two possibilities. When n is equal to 3, you can have 0, 3. We can have 1, 2. So basically anything within like this range will work. For n equals to 5, seems that we can only have these two possibilities. When n is 7, so if there are too many A's, then what we can probably do... Wait, no, this is stupid. Like, wait, why am I even doing this? So, the key observation is that... By the way, you can't have 0, 3. Like, that's just like messed up. Okay, so the key observation is that every time you remove 3, every time you choose 3 shards, like, they have to be consecutive, but it doesn't really matter. You essentially remove 1A and 1B from the entire sequence. So the difference between the number of A and B actually stay the same each time n decreases. So, which means that for a certain n, if we look at this pattern and like just generalize, it means that we can either have, the count can either be, it can either be this or this. It's the only way that, because these two pairs are the only ways that we will reach 0 only when the counts will only reach 0 when n is equal to 1. We can't have the counts reach 0 like before n becomes 1. So I think this is the only condition. Like, yeah, I don't see any sort of edge case or anything, so I'll just go on to writing the solution. Then we'll count like A and B. Actually, you'll need to count A. Like, just need to make sure that, because B like depends on the value of A. So the answer is yes if the count of A is equal to n minus 1 divided by 2, or it's equal to n plus 1 divided by 2, then print yes, otherwise you print no. Okay, this probably ran on like some file. So yes, no, yes, no, yes, no. Okay, I think we're ready to validate this solution. Should be good. I don't remember like Facebook Hacker Cup for containing too many like trick cases in the hidden test cases, so This should be fine. Maybe there's a plugin I can use to like do all of this efficiently. Output and oh yeah, source code. Okay, got B. So far everything's been pretty simple. Wait, they actually have pretty big constraints. I feel like the constraints have increased for like linear solutions. I'm not sure. Are the positions sorted already? I don't think they are. Yeah, I can just sort them later myself. Do we have to cut down a tree? The trees that are cut down will... I'm pretty sure there are cases where like no matter how you cut it, like the trees, if you no matter how you try to cut all trees, like there'll be intersections. So I'm assuming that you don't need to cut all of the trees. I'll just read it again to make sure. Oh, or it may be left standing. Okay, I see. I somehow missed that. Okay, so solution is, can P coincide? I think if all the positions coincide, like it'll still be fine. Yeah, I think it'll be fine as long as H is positive. Okay, so first we'll sort all the trees by their positions. Now let's like process the, we probably want to process the trees from left to right. So let's say that this tree will be the last one we cut down. So if this tree is the last one you cut down, then we have two choices. It can either fall to the left or fall to the right. And probably, well, we need to know, like, since it's the rightmost tree that will fall, we need to know that, like, we need to know the maximum length of, like, trees which fall exactly here, and the maximum length of trees which fall exactly here. No, exactly here. If we choose to, like, cut it to the right, then we can combine the intervals. So the way you do that is you probably do some DP to store, like, DP out of J means the maximum, like, length of an interval, which wait, is actually never mind then. Okay, we'll just store, like, we'll store DP of J, which means max length of an interval, like, which ends at J, while, like, which ends at J using the previous using the previous trees. And how we can use DP of J to find the answer. So let's say this position is X and this position is Y. And also by default, like, the DP will be 0. We can max the answer with DP of X plus the height of the current tree, and DP of Y plus the height of the current tree. And after we update the answer, we need to update the DP as well. So we updated DP for the first case, so DP of X, DP of X plus the height, which is the new end. We update that with, like, the last value and also the actual length of the interval, which is this. And then we do a similar thing for DP of Y. And DP, we can probably just store that in, like, a hash map. So now I'll just, yeah, in Java, sorting pairs is a little bit more, it's a little bit more inconvenient. I have to create my own pair class. This is called entire array A for no good reason. Reason, position, and then H. Okay. Now we sort. No, use arrays.sort. Okay, and then we have to also create a DP, which will be a hash map. And then we'll also store the answer. It's what we print out in the end. Okay, we start from I, and we just did the procedure I described above. So first, let's find x and y. X is, this gives me the position, and then to find the actual position, like the starting point where it lands, and you subtract the height. And then y is equal to just the original position. And we just max it with the two like values, dp.get or default. Trying to get x and the default is 0. You also add the height to the end of it. And we update the DP. But the key is x plus the height. Value we put is we basically just like take the max of the old value and also the new value, and then we do this for y as well. Actually kind of regret using Java. Like sometimes it makes things a bit more complicated. 9 shoot. I probably want to process these in order, just so that nothing bad happens. Like if I process them in like in increasing order, then what might happen is I might use the same tree twice. So I have to like process the right tree first, like cutting to the right first, and then I process cutting to the left. Then I think it'll be correct. 996, 1233, 80. Okay, everything looks correct. We can validate the solution. Okay, let's upload the output. Actually, I really should have. I don't know if I should have like created the. I don't know if I should have created the entire. That like created like c.java before I downloaded an input. Then maybe I could save some time. I don't think it's that important, especially not in the qualification, man. Timber input. Let's run. Okay, everything looks reasonable. Output. I actually need to fill c.java with something, with my code. Processing submission. Okay, now I'm left with D1 and D2. D1's probably easier. It should be easier. Solution to each chapter may help with solving the other. So, okay, I'll read both of them first. Okay, a tree. Oh, in a single line. Oh, basically like the first problem. Full gas of gallons. What's M? There's a linear solution, is there? I feel like the best I can do is n log n for now. Wait, actually, if I use a min q, okay, I think I should explain more what I'm thinking of. So I'm thinking is if you're pretty experienced with DP, you'll think of a DP solution. dpij is equal to min cost to get to city I with j gallons left. And then this is like n squared, which obviously won't pass. But if you consider the transitions are like really unique. So let me map I over here, and then I'll map j like on the top. So what happens is, if you're at 0, you can't transition. You can only you can't really do anything. So, and then if you're at 1, you can spend 1 gallon. So you transition here. If you're at 2, you can spend 1 gallon. Transition here. What happens to most of the transitions is that you increase I by 1, but then you decrease j by 1. And what instead you could do is, you can basically not you can really just store everything in a dpj, in one dimension. Oh yeah, also I forgot to say, you can also choose to buy gas. If you choose to buy gas, then what happens is you don't even need a min. Yeah, I don't. Wait. Okay, actually, I'm not sure. But what you could do is you take the minimum of all of these, and you plus C, the cost of refilling, and you go, and that becomes this new state over here. And so instead of going down, what you could do is you can do some sort of you can be lazy and just let the transitions go horizontal. So you don't actually have to change all of these values. The only thing you do is you delete the bottom value and then you update the new value. So if you do it like this, then the transitions can be done much faster. And just to reduce confusion, the next one will be even higher up. So essentially what happens is since the transitions are going down right, you shift all of the DP layers one up. You rotate it so that the transitions are horizontal, so you don't actually have to do anything. So you don't actually need to update the array. Like the question is like, do I need to actually find the minimum of the entire thing, or is the minimum just like at 0? Because if the minimum is just at 0, then that means that like I don't need that means I don't need a fancy like sliding window minimum data structure. And I can just like take the value of this and add C to it to find the new value of dp. So at the start everything is 0. I think I actually need like a stack for this or something. Because the new value could like, this value could actually be like smaller than some of the values here. So what I can do is, if the new value is smaller than the other ones here, that means that I definitely won't use these ones. So I'll just like delete them. And then like I'll delete them until like the new value is smaller. Basically I'll probably keep like, it's basically a queue which is like monotonic. So the prices are monotonic. Yeah, it's basically sliding window then. Okay, so I think I have the solution for D1. Before implementing, I'll check out D2 to see if anything. Oh, it's a tree now. How interesting. You have to start from A to B. It's not even. Wait, can you? Can you like revisit roads? Feeling. Yeah, so for a voice job, what you can do is you can actually like refuel, like you can actually visit a road twice. Like you might not take the shortest path, because the shortest path might not like be might not give you the cheapest price, as shown by this example. So what are the constraints here? Oh wow, they still put like high constraints for this. Okay, I think I want to solve this. Like, I don't really feel like writing separate problems. So I can't tell if it's supposed to be linear or if like, or the solution is supposed to be like n log n, or even n log squared n. Okay, so for these problems, like probably want to make some observations. I'll keep this here for now. This is like, I can think about a solution later if I really need to. So you have a starting node A, and then you might actually go back. So you have a subtree here. You might go back to. Wait, will you like? No, you never go back to, because you start from A with like a full gas tank, right? And with a full gas tank having a capacity of m gallons. Okay, so if you go back and come back here, you're gonna have like less gas, so it's kind of pointless. So everything in the subtree of A, you don't need to consider. Then you have some nodes. And then you have B. And again, it's kind of pointless to go past B. Like, so everything in subtree of B, like, we just won't consider at all. Okay, so now what happens? Like, what happens in the subtrees here? Is it true that like the optimal route will look pretty simple? And by simple I mean that like basically it just goes down a path and then it comes back up. Like could there be a case where like it goes into the subtree, refills and like refills twice? Yeah, okay, so I guess what I want to consider is if I go down a subtree here, like is there a possibility that I want to refill twice in the subtree? So maybe I go down here to some node 1, then I go back up, go to node 2, and then I go back again. So is this case ever possible? Because if it's not possible, then it'll make like my life much easier. So so let's say the distance from this node to 1 is x. Like the depth of node 1 is x, depth of node 2 is y. Then like one has to be shorter than the other one, so if y is shorter than replacing this with like just going to node 2 will work. But if x is shorter, then if somehow x turns out to be shorter than like why bother going to y? Like we can improve this, like without loss of generality. If y is shorter, then we can improve the solution by just like replacing like going to 2 nodes is just going to node 2. Then like because y is smaller than x, this new route will also like work. You won't run out of gas using this new route, and like it's also cheaper because you don't go to an additional gas station. So yeah, so okay, so it seems like we only go to like at most one refill at most once in each subtree. Hopefully I'm not wrong on this. Okay, so now this is kind of like an extra addition of, this is almost like a linear thing, but it's not quite the same. I think we still use a DP to solve it, but instead of transitions here, so if node 2 has cos c, then you have this transition which I'll describe as a pair YC. This means that you transition in with like at least y gas, and then what you go out is with you go out with like you already used n minus y gas, and then you add c. So actually I think that this is a segment tree DP. So using the optimization I described earlier, so first of all, we don't want to consider the transitions where where j decreases by 1. So we modify the indexes so that j never decreases. So like barely anything gets updated, and we only increase like the starting position of the array. But then like all the transitions are just like, this is like query on a minimum, which we can easily do with a segment tree. This is like setting on like setting a value on a particular index, or like we're actually taking the minimum, but it's kind of the same. So you can also do that with a segment tree. So okay, how big does my segment tree have to be? It's like by the ith node, by the ith node, my thing will start with it'll start at I minus 1. No. Wait, no, it'll start at I, yeah. So the actual DP array will start at like index 1 of the segment tree here, and here it'll start at index 2 of the segment tree. So at the end, this will be the start array. And then we also have like the possible M. M is given, right? Yeah, it is. So, and here we'll have n plus m minus 1. Yeah, that makes sense. So in total, the segment tree should have length n plus m. And then it should be like range minimum, and then range minimum queries and like point minimum updates. Okay. So how do I write this so that like I don't waste any time on like, because the input is quite different for both of them. So I think the abstract problem here, we're given we're given like we're given for each of the intermediate cities, so v of 1 to n. Like we're given these pairs of like how you can transition. Given these rules of how you can transition to the other pairs. Okay, that makes sense. Yeah, I might want to process these transitions in a very specific order. Do I? Does it actually matter? Okay, I should put the plus c here just for clarity. I can like query all the minimums first before updating anything. Then I think that'll work. Okay, so the abstract problem here is nm and then this. So I'll call that so actually I'm going to have a solver 1 and a solver 2. So these two are the input classes, and I have the main like solver function, which actually into m, and then a list of pairs list of pairs, an array of a list of pairs, V. And then, okay, so in this solution, so segment tree, I'll use like, there's a code forces blog about like easy and efficient segment trees. Do I want to create another class for that? Yeah, sure, why not? Also, there's a catch. I need long longs. Probably. Like, the answer could probably be like n times c. On the order of like that magnitude, so. Fill this with like lambda max value. Okay. Then we have our update function. So, no, the range minimum query function. Yeah, write the update function first. So, index I and long x. It has to be greater than 0, okay. And then the query function, we query from L to R. For now, I'll make like the right bound inclusive, which means I need to add n+1 here. Oh yeah, I can't use this value. I use B then. A of L, I think. Then if R mod 2 is equal to 1, then A of R minus 1 B. So this completes my segment tree. Am I not allowed to do this? Because in C++ I am allowed to do this. Okay, that completes my segment tree function. Initializes everything to infinity, not okay, infinity. So our initial state is we has a cost of 0. And to be honest, first, what's the answer of the entire thing? It's probably like we query n minus 1 all the way to m plus m minus 1. Yeah, okay. Okay, so we have our transitions. Here, I kind of want to make the pairs, like, actually name them correctly, so there'll be a Y and there'll be a C. Like basically like what I wrote in my notes. And then these will be the ones I want to update. So after I calculate the transitions that I want to update the DP with, I'll just update them in the array. So like the next index will start at I plus 1. That's like the offset. And then the actual index will be Y. And we update that with the cost. And in order to find the pairs, I'll go to the pairs given like over here. So the new index is m minus y. So I just realized I probably don't want like max value. Infinity, I'll set that to like 118. Because max, like if I add anything to max value, it's going to overflow, which is not good. So you update index m minus y. And then the value is, so first of all, there's an offset of I for in the segment tree, and everything greater than or equal to y. So go from p dot y all the way to m. Like this is the current range of the segment tree. Yeah, this makes sense. Okay, I think this is correct. Hopefully it's correct. Now I just need to write the input functions. So for this, n, m, and then c. Okay, and then we create the array of lists called V. I'll make it, it doesn't really matter what size it is. And then if there's a, like, if we can refill, then we add the pair for the transition. And why is 0 like in the first case? Like you don't travel down the subtree at all. I just call new solver nmv. And yeah, this should be good for D1. Oh, there's also the case of -1. I never thought about that. Okay, so if the answer is greater than or equal to infinity, then it's greater than or equal to infinity, then it's impossible. Otherwise, I just output the answer. Okay, otherwise everything should be correct. 2020, 20. Something did not go correctly. Could be like so many things could have gone wrong here. I think what I'll do is like after everything I'll print the DP value. Case 1, you start this, and then you can refill for 20. That part of this doesn't make sense. Wait. 1, 2. Oh, maybe you don't add 1. Is this the issue? Yeah, I think it is. Oh, okay. Like I don't shift before. I need to shift after. 20, 30, -1. 50. Okay, this looks correct. But since the time penalty is like your last submission, I'm pretty sure I'll solve D2 as well, so just in case something's wrong with my DP, like I might be able to catch it while solving D2, so that's the reason why I'm going to submit D2 first. And the only because of the way I've written my program, the only thing I need to change is like solver 1 to solver 2. So this is a bit more complicated. You're given a tree to work with. Okay, next thing I need to do is PI and CI. I'll create a adjacency matrix list. And then, yeah, basically add so see that I want to store it globally. I think that'll actually be like, I think it'll be a good idea to store it globally, because I might need to like use it in certain DFS functions. And they should have just given the edge format for the tree. But anyways, doesn't matter too much. The first DFS, DFS1, we try to find the path from A to B. So let's have a boolean, which means like is a certain node on the path from A to B. And then we'll also have a list of like the actual nodes on the path. And both of these we'll find during the DFS. So in our DFS function, returns true if we have found a path here. So current node, the parent, and we have a target. First thing we do on path u is equal to true. We add it to u. But it's only when we don't find a path that like when we exit this node, we'll remove like them both from we'll remove both of these from we'll remove this node from like both like data structures. So if u is equal to target, then we found our target and we can return true. Otherwise we iterate over adjacency matrix. If v is not equal to the parent and we found our path from v, then we return true. Okay, this gives us our path. Next thing we need to do is create the array of pairs v. It's not actually n. The new size of n is just the size of the path. So what I'm going to do is go in DFS2 from the node. It's going to be a parent. And then it's going to be at depth, which I'll use to calculate y. And then finally I'll pass in this like list of nodes, list of pairs of like transitions into the DFS function. And then DFS2. The depth, and then the list. I should not call it V. I'll call it W, whatever. So what did I do? Oh yeah, I checked the current node. So if it's greater than 0, then we can add a new pair. This pair will be, the depth is the first element, right? Okay, so depth and then the cost. And then we iterate over the children. V is not equal to P. And P is not like on the path. Reason for this is because like I don't want to, like if I start DFSing from this node, I don't want to like go to this node. Like I want to make sure that like the node I go to is not like the next or previous node on the path. So it's not on the path. And what else? I think these two are the only conditions. And I go to this node. The depth increases by 1. And yeah. Lastly, I call solver with like these new, like with all this new data. Okay, so it looks like I've finished my first iteration of this code. 48, 160, 20, 104, 17. Okay, everything looks good. Let's submit D2 first. What was it called? Running on fumes. Okay, let's validate it. Oops. Okay, let's validate it for D1. I need to make sure I change it back to 2. Like, I don't know, I could like accidentally forget to change it back to 2 and then everything could just like all this hard work would just go to waste. Oh, I downloaded it already, so what's the point? Let's go output. Okay, now I'll create D1 and D2. I don't know if they actually run the solutions later, but like, who cares? I'll just, it's a bit inconvenient, but I guess Facebook doesn't have good enough servers to run a proper contest. Okay, where's my input file? Please give me my input file. I did paste this, right? Okay. Run configurations. Chapter 2 input. Let's run this. It should take a while. And hopefully nothing crashes. It seems like nothing crashed. So output source code D2, submit. processing. Okay. Now we'll submit for D1. Oh, I almost forgot to change this. Like, okay, like the thing will crash, so it's fine if I like. It's fine if I forgot because the input format is different, so I think it should crash if I forgot to change it. 85. Shoot. Output. And then d1.java. Submit this. And I think that's the end of this. Rank 192. Even after 2 days. I don't know if that's surprising or not. I'm not sure. But anyways, yeah, things could change because like you don't know if your submission is correct or not. So anyways, I hope you enjoyed like this type of where I actually talk more and where I actually explain my solutions more, both like while thinking and while coding. And if you made it this far and it actually helped, then please like leave a comment in the comment section below to let me know that this helped, and I'll consider making more videos like this in the future. Goodbye.